So this is so far what we have. And the function we had started with was, this function in y of x, and I'm going to put it on the board here in operator notation so we get a good idea of how we do our tables and so on. But we were told to graph this. We identified a few things, and there were some keystones dealing with this. Primarily, if I was to lay out what the keystones are of this, that's what I'm about to do before we kind of continue on with this. And those being mathematical key steps, right? So one of the things that we did last time, just to not have to rehash things like massively, let me see. This is acting really weird. Hi, thank you. If we go back to our previous, one of the first things we did is we evaluated the numerator. Now, you're not always, sometimes you're given the function in the form, the expanded form, the factored form of the rational function. So I'm going to put that work kind of like right here and how it can be like presented differently. Give me a second here. There, Aladdin or Sal. Can I call you Sal? All right. Here's what we got. So if we expand this out, naturally, we shouldn't have to go through that process. But let's just say, for example, that you were given, let me shrink this down as much as I can. I'm to really have to deal with just one monitor today. But let's say you're given the function. Let me make this a little, there we go. Span this out. So they'll typically give it to you actually in the form, like on test and things like this. They'll say y of x is equal to, and just to make it clear, I'm going to specify how I go through the analysis separating the numerator and the denominator. And, I do expect a little bit of kind of common sense in regards to how I am doing that. Respectfully. So you've got this over, they may give you something like x squared minus x, right? And then so that's how it's usually presented. And then what you'll have to do is, factor this guy. Typically, that's how they want it done. So we group these. And so they give it to you like this, and we will have to, sorry for that little dot there. I don't know what that's doing there. It's weird. Okay. This is the worst thing for OCD, a dot. Okay, so this is what we need to get to. And so what we do, we're going to just take an x out of the denominator. But before I get to that, we're going to label what our numerator and denominator is so that we don't lose our work. And we know that the numerator tells us what's the keystone?
Right.
It tells us the roots, right? That's right. So this tells us
And
the
the denominator
roots.
tells us the vertical asymptote.
Very good. And so we know that the roots are zeros. So what are they?
Right. So the roots for this one were 2, -2, and -3.
Good job. And just by looking at that, well, yeah, no, it would be x equals 3. If we look, it's always the opposite. X equals 2 and x equals minus 2. Very good. And we know that the denominator
is a vertical asymptote.
Tells us the vertical asymptotes. And I'm just going to abbreviate that here. So vertical asymptotes, VA, I just call it VA. And there is defined as the zeros, right? The vertical asymptote, or you can call them the singularities, really. That's really what we would classify them as. And that means when I say singularities, it's more specific. It's more unique to what's going on. That means division by 0, right? So when you put that number in, if you put in 1, that gives you division by 0. If you put 0 in for x, that gives you division by 0. So this gives you the definition for vertical asymptotes or singularities, or division by 0. That means it's the zeros, right? The only difference is that it tells you the asymptotes, where the numerator tells you otherwise. Now we can do the long run behavior as well and all the rest of this stuff. But before we get to that, right, the short run behavior, and we also have the long run behavior. So let's go ahead and do this. So we know that the numerator, right, I'll just say n of x is equal to x cubed minus 3x squared minus 4x plus 12. And what we did, in order to, factor this, we use synthetic division, right? It's very useful,
because
right?
The numerator is greater, the power of the first term is greater than the power of second term of the first of the
Yes, right. They reduces it down. We just keep repeating the process for this term, or you can just back factor by looking at or use the AC method for the easier 1x squared. So we have videos on that. So that's what we did. We did that to get our zeros in the first step, right? And then I could really kind of just lay it all out and say, okay, that was this work here, right? And then real simply put, if I wanted to solve for the zeros in the denominator, division by zero, right? If I wanted to, I could just look at it, or I could just write it out. I could say, okay, we've got x times x minus 1, right? If you take an x out of this. And we set that equal to 0. That way we know that x is equal to 0, and we know that x is equal to 1. These are the two singularities. So then now we have this really simplified down in terms of y of x, and this is one of the most useful forms you can use for plugging and chugging with these things. So I'm going to move to the next screen here. Now that we have that down, we have the two keystones for that. But now there's so many different mathematical operations that we can get to when we're dealing with these. But if what we can do right now is we might just put our vertical asymptotes on the graph now, and I just have the graph here. For convenience sake, you may not have it, so I'm just going to try to mark this up since we're going to pretend like we don't actually have this. But I like to have it there so y'all can see it. One of the asymptotes is going to be at, of course, x equals 1.
Yeah.
And the other one is going to be at x equals 0. So we just kind of do these little dotted hash lines here.
Right.
And you can label them x equals 1, x equals 0 for division by 0. Now we know our roots for this one. We've already done that. We've got 1 right there, right? That's going to be at x equals 2 and x equals 3. And we got 1 right here at x equals minus 2. So I'll just label those instead of doing x equals so don't run out of space. And that's 2 and 3 there. Okay, now you're not going to see the lines on the graph, right? So now we have to ask ourselves at this point, we've got vertical asymptotes, we've got roots, and we have not so much a horizontal asymptote, but an oblique one. Hey.
Yeah.
And with in order to find the oblique asymptote, what do we do, Zaid?
To find what asymptote?
The oblique asymptote. What do we need to do with that function right there?
Well, in order to find an oblique asymptote, you only find it if the power of the numerator is greater than the power of the denominator.
Very good job. There are 3 rules. The first rule is that...
the one is that wait for the oblique.
Oh yeah, so yeah. The first rule was what? The first rule was you take the numerator and set it equal to, wait, hold on, sorry. The first rule was if n is greater than m, and it really doesn't matter what your trailing terms in the numerator or denominator. This is the most important part of the formula. You look at your leading terms and the highest power of x for your polynomials. If you don't have it written out in descending powers for the numerator and the denominator separately, then of course, logically, you're not going to see those leading terms and you're going to get it wrong. And so in the first bullet, if your denominator's power is greater than the power in your numerator for the leading terms, then your horizontal asymptote is going to be the x-axis. And for information, that's y equals 0. And if n is equal to m, then your horizontal asymptote is the leading coefficients a over b. But in our case, we have a very unique situation, which is less common, and that's when the coefficient in the numerator happens to be greater than that in the denominator. And we've done that before with long division, but that's exactly what we do in order to find our oblique asymptote. So now we really kind of see if you were given a rational function and 2 polynomials, that when you're using long division before, right, you were taking something smaller into something greater, you were actually finding that reduced form. You were finding an oblique asymptote geometrically on the graph without even knowing it. So that's usually why we teach that first. So if we go to the graph, then we can see that right here is our oblique asymptote, and we're going to go through the process of knowing how to do that. And so in order to find that, we just simply divide, and we need the expanded form for this, actually, don't we? So let's go ahead and grab that. Okay, I have a
You
little
mean like
arrow
x
there.
squared minus x? That
That's right, because it would be senseless to graph. You can't do long division in the expand. I'm sorry, in the factored form, right? We have to do it in the expanded form here. So what we do is we take that long division. So you've got x squared minus x, and we divide that into that entire thing. And what we do is a we'll
we'll
get a
get a remainder for
formula,
sure.
yeah, that will tell us the formula for the oblique asymptote. And so, what do we know about horizontal asymptotes? Horizontal asymptotes and oblique asymptotes, right?
Right.
They tell us the long run behavior,
The long one be. Okay.
right? And that's really what happens when x. What's going on, right? What happens to y? Y whenever x goes to negative infinity and positive infinity. We want to know. So that's what it tells us. And really, we can kind of see that behavior right here in the oblique asymptote, right? It kind of takes a portion, skips over the other asymptotes, right? And it's
Yeah.
really defined as that long in behavior. And it makes sense when you do this because when you do it, you will have a remainder, but that remainder disappears. So we really like it's kind of, I want you to think science, right? What's going when x is going to negative infinity, right? As it approaches negative infinity. And what happens when x is up here approaching positive infinity, right? We're not so really that much interested in what's going on before the roots and the asymptotes. We're trying to go a few pegs out to see where that kind of starts and kind of, you can think of it as like kind of switching on. As a scientist applying math, you might split up your graph and it just kind of depends on what's going on in your system dynamically, like if you're modeling populations and so on and so forth. But so we go ahead and we guess this and we get x cubed. We do our long division on this.
And then okay, so that's the x times it's just be negative 2x squared. No, negative
Okay.
x squared, excuse me, sorry. And then after that negative 3x, so that's positive 0, so it's going to be negative 2x. No, negative 2x squared, right?
Wait, the 3x squared, x
There's a
times
minus
that
here and
is,
a minus here.
that's a positive. That's very correct. So that is going to be negative 2x squared. Very good.
After I bring down the negative 4x,
Okay,
then,
yes.
then after that, then after that,
What do we guess? Probably a 2, right? A
yes,
negative
2,
2?
yeah, 2,
Is it negative
yes,
2?
negative 2,
Yeah,
yeah, negative 2. So
right.
negative 2 times is again negative 2x squared, and negative 2 times it's going to be, uh,
Wait. Yeah, that's correct. Very good. Wait a minute. We want that to cancel. So if it's a negative 2 here and negative 2x squared, we'll have our negative. Very good. Very good, Zane. Very good, Sal. So now we do the rest and we get our positive 2x
yes,
there. These cancel to 0, of course. And then this is going to be, what is that?
2x plus 12.
If I drop the negative 4x, I've got the negative and I got to distribute the negative out here, right? So
Yes.
perhaps maybe that's negative
Well,
6x?
wait, no, negative 4x minus, wait, negative 4x plus 2x is negative 6x.
Yeah, but
It's
you
not
have to
negative.
distribute the negative sign, right? Right here.
Okay.
Yeah.
Okay, yeah, I see.
So then now I know sometimes, when your brain is tired, you're doing all of these things, you look at something simple that you've done before and you're like, whoa.
I mean, I guess we can graph, we can
But here's
reduce
the
that.
thing. We are, so it doesn't have to be, what were you going to say? Sorry.
I was going to say that we can't reduce it out any longer. So it's going to be x minus 2 minus 6x plus 12 divided by x squared minus x.
And what do we know about that remainder over the divisor there? We know that these are the two leading terms, and if you reduce them down, right, then conceptually, and this is completely legit because it really doesn't matter because as x gets larger and larger, this thing keeps going and going, but the small part is always going to drop out because this reduces down to 6 over x. And as x gets really large, right, this remainder
Yeah.
portion goes to 0, right, eventually.
Yeah.
as x goes to positive or negative infinity. Now, you really want to check negative and positive infinity separately sometimes, but in this case, it's just kind of directly straightforward because that's going to drop off, and this is just going to be increasingly more negative and large if we go to the left, and this is going to be increasingly positive and large if we go to the right. So this base becomes approximately the oblique asymptote x minus 2, and it really switches on somewhere around from, and it doesn't have to be perfect, like negative 2 to um, somewhere close to that, negative 2 to negative infinity, as well as somewhere toward like 3 to positive infinity. And you really don't have to write any of this down, but at least it gives the user the idea that, hey, this is the long run behavior. Does that make sense?
Yeah,
And
so
so
you just
for
found
on your
out
graph,
here.
we don't really have the curves on this, right? We just have these curves I have there from the computer, but you really just have the vertical asymptotes and the oblique asymptote, right?
Mhm.
So that's the whole point of the table, right? Because the table kind of fills in the gaps for what we don't know. Now, in calculus, you can learn how to graph that in most cases. So, in this case, more than likely, that would be graphable using calculus, right? Taking the derivatives and
Right.
so on, but we haven't got to that, right? So, in other words, in this scenario, a table is really your best friend, but you really want to get most of this analytically before you engage in, plugging and chugging these numbers. And so I have this table in my calculator that I spit out here, and this is what we get. So we can now kind of fill in the gaps for the closer points, and we've got -1 is 6. So that's interesting. So if you've got -1, you've got 6 right here, something close to it, right? And so that gives you a point, right? And your asymptote's doing this, so that kind of gives you a point right there. So you really have three really solid points that you can kind of trace through, right? And you start to see this behavior, right? We're going to put this graph together. Does that make sense?
Yes, that makes sense.
And now, so we can, I'm going to shade those in gray, kind of, I mean, green there for what we just did to kind of solidify all this. And there's over there too. We also have these 2 points right here that kind of help. So you've got this, so far you kind of have something like this. You may not know, but if there's a block there, we really have this portion there and that for the long end behavior. Now, if you go to the value 4 is equal to 1, then that's really that point right there. But what happens when we get to somewhere, and this isn't like where I have it, I really wish I had this portion of the table. But what I'll do is we had a table from last time that we did by hand, and I think that was 1/2. You did it for us was -37.5, but that would be incorrect, or it may be correct actually. I take it back. That is no, that would be incorrect. So we need to look and see what happens when we get really close to that asymptote at x equals 1. So we might put something like, let's think this through, like 9/5 would be a really good value because it gets to 2, but it's greater than 1. And we see this gets exponentially large. Now, you're not going to know that until you plug a point in real close in between your root and your asymptote, and that'll give you an idea. So in between 1 and 2, you can do 9/5, or if this is 1, you can do like 6/5. It doesn't matter. So I know I said 9/5, but let's try 6/5, right? Let's see what that gives us in our. So if we plug it into our function, and I would encourage people to do this at home, um, we're going to get this 96/5 as the value, and that's really massive. So let me go ahead and get the number. You'll definitely need a calculator, at least a handheld for that. So let's go ahead and
So
grab
I'm looking at
this.
my calculator. What's the number?
6/5. We want to plug that into the entire polynomial, right? You can plug it in this one or this one, it doesn't matter.
Well,
And
I used for the table on slide 2. I used the values here, the roots.
yes, but the point I'm trying to get at is you don't have this. What's important for you, you need to pay attention here, okay? Respectfully.
Okay.
Pay close attention. We only have the green and the blue shaded in, and the pink and the asymptotes. We don't have the blue that came from the calculator's graph yet. That means
Oh,
we need something between the root and the asymptote. Are you understanding? We need something in this small gap right here.
okay. I see.
So this is for the gap between the vertical asymptote and our root. So always look for your gaps, like those really small gaps that give you really relevant information, especially as you get close to the asymptote. Because really this approximates down to what, 1.2, I think. So then at the value 1.2 for x, you have 19.2 for y. That's pretty big, and that gives you a lot of information because it's like almost off the charts. That's up here. Now, what's really great about that is that tells me that earlier on I had this small bit and I have these asymptotes. So I can continue on with this graph. And then I can look right here and I can just continue on with this where I can bridge my roots to that and the end behavior. Now it's complete. So now you see, that's how we kind of graph these. And that last part was just kind of picking from our table a few values. In this case, we really only needed -1 and 6, right? We could have like -3 and got -2.5, right? That would have been okay as well. So I'll kind of like circle that in, kind of like that. And then you have maybe, we also had this was between them. And we also have our long run behavior and we have our roots. These are all like very useful points to put in here in our VAs, right? So that's really all we need to graph these things. And 4 and 1 was that long run behavior portion. We really didn't need that, but you can for safety's sake, and you do the others. So, but most of these were done from finding our roots by factoring or by using synthetic division, the zeros, and then the VAs by just, pretty simple down there, just taking out the x and setting those equal to 0 to find those singularities. And by definition by 0, you would be solving for the zeros in the denominator for the VAs. So that gives us everything we need to graph these things. I hope this helps. And yep. Jamata mata.